All right, here we go, guys. This is the last video that I'm going to be making for your final in physics. Here we go. Congratulations, you made it to the end. I'm going to erase a little bit. There was something left over. So we have the first page, which has to do with the conservation of energy. And all we need to know is that the total energy in the system, the ME, or mechanical energy, is equal to the kinetic energy, energy of movement, plus the gravitational potential energy in the system. Now, this guy over here, number one, is all the way down on the ground. He's not up in the air. He's not up high on the ramp at any point. So if his height is 0, then when we try and figure out potential energy, it doesn't matter what the mass or gravity is. That height being 0 makes the whole thing 0. So there's no potential energy, no joules of potential energy. So what do we have to figure out? Well, we have to figure out how much kinetic energy is in that system. And we have mass and we have velocity down here. And we'll just use this formula right here. So if we can figure out that the kinetic energy in this system is the mass of the object, which is 60 kilograms. And I lied, it's 1/2 of that, right? 1/2 60 kg times the velocity, 8 meters a second, squared. Okay, well, I'll take half of 60 because I know that. And so the kinetic energy is half of 60, which is 30 kilograms, times 64, that's 8 squared, right? Times 64 meters squared seconds squared, and that's our unit for joules, right? And then 30 times 64, we've done this in class, so I do remember that kinetic energy in this system happens to be 1,920 joules. And so for kinetic energy, we'll write 1920 joules, right? Okay, so the next piece is, well, let's add 0 plus 1920, and that gives me my mechanical energy. And we'll just copy that 1920. The conservation of energy states that no energy can be created or destroyed within a closed system. So this is a closed system. It's just that person riding a skateboard, and we're going to discount or ignore any friction or anything like that, or any air resistance. We're going to say the energy is going to be the same throughout. So ME being 1920 here, it's going to be the same here. 1920 joules, and ME will be 1920 joules. All right, so we're going to move on to this guy. And there is some potential energy here, right? There's some potential energy because they are 1 meter up. So I can use the GPE, or potential energy formula, to find out what that potential energy is. So at 2, this was number 1. At 2, we're going to say the PE, or GPE, is going to be equal to the mass, 60 kilograms, times gravity, 9.8 meters a second squared, times the height, which is just 1 meter, right? And believe it or not, when we do this math, PE equals 588. Remember that 588 because it's an important number. We're going to use it later on. And then what we're going to do is we're going to subtract 588 from 1920. And if I'm not mistaken, I think it's 1332, but I'm going to go ahead and use my calculator. And I was right. It is 1332, 1,332. So I can fill that in. Why? Because this plus this has to equal this. That's what it says here. Kinetic times potential has to equal the mechanical, which means I could say the mechanical minus the potential gives me my kinetic, and that's how I found that kinetic energy there. We can now use this kinetic energy to find how fast this skateboard is moving or this skateboarder is moving by rewriting this and solving for velocity. And trust me when I tell you that the velocity is equal to the square root of 2 times the kinetic energy divided by the mass. Does that look like it? Yeah, the 2 gets rid of the half, divide by the mass, and then take the square root. Yeah, that's exactly what we're supposed to do. So I take this velocity and I say it's the square root of 1332 times 2 is 2,664 divided by 60. And I seem to remember it was, I have it up here, 6.7 meters a second. 6.7 meters a second. Okay? And we could have said that this is kilogram meters squared seconds squared, or joules divided by kilograms, and that cancels that out. And then take the square root of meters squared seconds squared, you get meters per second. All right, now we'll move on to this last guy. And what I'm going to say is, since we are not given a height here, there's no height given. That means we're going to be looking for the height, and I'm going to say that the velocity is 0. Well, if the velocity is 0, then there can't be any kinetic energy because there's no movement whatsoever. And I didn't mean to write that. I meant to write joules. And then that means that all of this is potential, and he has come to a stop and is ready to come back down. So I want to find out what the height is. Well, I take this 1920. So I'm going to say my potential energy, 1920 in joules, is equal to the mass times gravity times the height. So if I want to just solve for height, I divide by mg, divide both sides by mg. And we remember that mg is 588. All right, and that is going to equal our height. And if I'm not mistaken, our height should be just about 2.3. All right, and I'm going to look one more time just to make sure. Yeah, 3.2. Sorry, 3.27. I'll say it's 3.3 meters. Sound good? Pretty simple. We can move on. Hopefully I have my, thank God. I do a little bit of erasing because I have to move on. Wow, that was fun. Oh, look at that. Move on to the next page. We're gonna do 1 or 2 from each page so we can get an idea of what it is we're gonna be looking at. So I go here. I apologize for the little kids yelling. There's a whole extra page of that. Yeah, I'm going to do these first 2. Why did you do that? Why did you do that? We did so great. We were so close. There we go. All right, I want to show you the formulas. The next page is conservation of momentum. And we have our momentum idea here. So momentum is P, and P equals mass times velocity. And the conservation of momentum says the net momentum in the beginning is going to be the same as the net momentum at the end. So we're going to take each of these pieces and we're going to add them together. This is before. These two freight cars, one is moving into the other. They're going to connect and then they're going to move afterward. I'm going to ignore tons. I'm not going to mark it as a T because that's later on when we're talking about temperature. So right now I'm just going to use this 10 times 4 meters a second plus 30 times 0 meters a second. And that's how much momentum, combined momentum or net momentum on this side. And this is just 0. So 10 times 4 is 40. And then that's going to be equal to the net momentum on the other side, right? So we're going to add these two masses together, and those two masses together are actually 40 tons. I guess I could say ton meters a second. And then 40 tons times the final velocity. And how do I get final velocity by itself? I divide by 40 tons. And that cancels out with that. And final velocity divide by 40 tons. That cancels out with that. And 40 divided by 40 is 1 meter per second. So these two things together are moving at 1 meter per second. Okay. So that's good. I would do the blob problem. It's the same. Let's talk about the referee. So I'm going to move this just ever so slightly because I want to talk about this perfectly elastic collision. It says, and hopefully you can read it, a football player runs at 8 meters a second and plows into an 80-kilogram referee standing on the field, causing the referee to fly forward at 5 meters a second. If this were a perfectly elastic collision, what would the mass of the football player be? Here's how it works. We're going to say the momentum on one side is the football player. And so we're going to say the momentum of the football player is going to be equal to some unknown mass times 8 meters a second. And since it's perfectly elastic, it means that he runs into the referee and stops moving, and the referee takes all of that energy and moves. Okay? So the referee is 80 kilograms, and he moves at 5 meters a second. Okay, well, if we do this math, I have 8 meters a second times m of the football player. And that's equal to 80 times 5. Hang on one second.
Story and Nikinsky report to the guidance office. Thank you.
Okay, so 80 times 5 is 400 kilogram meters a second. Well, if I want to find out what the mass is, I just divide both sides by 8 meters a second. So this unit cancels out with that. This becomes a 1. The mass of the football player is equal to 400 divided by 8, which is 50 kilograms. And there you go. There you have it. All right. These are arrows for direction. We can do that real fast. But I'm going to move on because this is going to be a very long video. Actually, I'm not going to move on. I'm actually going to do it. Okay, it says down here, two blocks are moving in opposite directions and they collide and stick to one another after the collision. What is their combined speed after the collision? So we find out what is the momentum of this block. Well, it's 8 meters a second times 1 kilogram. And we'll call this movement to the right, since we like right being positive and left being negative. We'll leave it as positive. So this is 8 kilogram meters a second. And we're going to add to it this one. Well, it's going in the opposite direction, right? So it's going negative 1 meter a second times 2 kilograms. Well, so that's minus 2 kilogram meters per second. And so their combined momentums are 6 kilogram meters per second. And so that's our initial. And that's going to be equal to this final, which is, I don't know what my final velocity is, but I do know what their combined mass is. 1 plus 2 is 3 kilograms times their final velocity. So if I just divide by 3 kilograms, there I go. 6 divided by 3 is 2 meters a second. That's my final velocity. Okay, there's a lot of noise going on right now because that was the final class of the day. I'm going to take a little bit of time to erase, a little bit of time to let these guys move through the hallway a little bit, and then move on to specific heat. There are a few types of problems that go along with specific heat, and of course I have to do this again because I don't know how to scroll, apparently. There we go. Specific heat is here. Excellent. Here we go. So, specific heat. Walk over here and let these guys do their thing and make enough noise to wake the dead. Remember, our specific heat was Q, and it was MC delta T, where Q was heat / thermal energy. Right, that's what that is. And C, or CP here, is specific heat. And specific heat is the amount of energy needed to raise 1 gram of a substance up 1 degree Kelvin or Celsius. So the first thing we're going to do here is we're going to find the specific heat of this little bit of iron that we have here. I'm going to rewrite this formula to make it easier to find. So the CP is going to be equal to Q divided by the mass times the change in temperature. Okay, and if I write this all out, I can do the math and I can find out what the specific heat of this iron would be. So it tells me that the heat energy in this is 1,086.75 joules. It also says that the mass of this iron is 15.75 grams. And we're going to multiply that by the change in temperature. It goes from 25 to 175, which is 150 degrees Celsius. Okay, so if I do a little bit of math, it's going to take me a little bit of time. Let's see. If I don't think I had this calculator with me when I did this. So let's do 150 times 15.75, right? Right, and then I can write this out properly for you. I have 1,086.75 divided by 2362.5, 2362.5, and that is grams degrees Celsius. And this is joules, right? And look at that. That looks just like this guy right here, doesn't it? Excellent. Okay. So if I do this math, 1086.75 divided by 2362.5, I get out 0.46. So 0.46 joules per gram degrees Celsius. Sound good? There it is. And then there's one other type of problem. There are a couple of temperature problems. This one is very straightforward. You just find the change in temperature and you put in the 10 grams and you put in the specific heat. You multiply everything all together and you'll come up with the actual joules of energy needed to heat up that amount of aluminum from 22 to 55. The last one I want to do is number 3, because this is it. I may cut this down. There are a lot of pages of this, so I may cut this down. Number 3, there it is. Okay, well, it was there until I let go. Where are you, number 3? Oh, that's why. Okay, we're there. Please. Please. Okay. And it says, to what temperature will a 50-gram piece of glass raise if it absorbs 5,275 joules of heat, and its specific heat capacity is 0.5 joules per gram degree Celsius. And it says the initial temperature is 20 degrees. Now, what you're going to do is you're going to solve for the change in temperature. So you're going to say the change in temperature, the T, the temp, is equal to Q divided by the mass times the specific heat. Okay? So what's our mass? That's our mass. This is our Q. And this is our CP. So Q is 5,275 joules over our mass, which is 50 grams, multiplied by our specific heat, which is a half a joule per gram degree Celsius. And it's 5,275 divided by 25. And what we'll end up with is some sort of degree Celsius. Because joules cancels with joules. And here we go. So I didn't do this one yet, so I'm going to do this 5275 divided by 25 gives me a change of temperature of 211 degrees. 211 degrees. That is a lot of heat. That's a big change of temperature. Now, it's not just 211 degrees. Remember, we have to add that 20 to it, right? So 20, 211, 231 degrees. Degrees Celsius. And that's it. Those are the types of problems that are on this exam. There's nothing else I need to do for you. Study hard, work through this stuff. The formulas are on the test. You're going to do great. And if you don't do great, that's okay too. Just make sure you show me you learned a thing or two. I won't be mean to you. All right. Thanks for your time.